Hello everybody, how are you doing? Hope you find yourselves doing great. My name is Gonzalo and today I'm going to be teaching you guys a little bit of organic chemistry. What is the goal of this playlist? It's really just to kind of brush up on some of the important topics. I've been teaching organic chemistry for 3 years now and I've recognized many patterns that some students struggle with, and I just want to kind of hammer through some of the basics that might be useful. It's meant to be a quick recap, a quick brush up on those who already took organic chemistry, those who might be about to take it, or even if you're midway through. I'm going to be incorporating many of the common topics that teachers teach, and also I'm going to make sure to explain where it might be different in different courses. So without further ado, let's get started. So I'm going to do a little brush up on, and also I'm going to be assuming you have some general chemistry background, although I will be pointing out some important aspects in case you forgot. So let's start with electron bonding and Lewis structure. So in general, electrons exist in regions of space, and a way of explaining that is Bohr's model. So Bohr's model kind of states that energy levels matter, right? So electrons exist in different energy levels depending on the distance from the nuclei. That's kind of one of the main aspects. So we can kind of imagine that they exist around an atom, and electrons occupy different energy levels in regions of space around this nucleus. It's kind of like you learned in Gen Chem, and the general order is that shells are the biggest thing. You can think of this as the house, whereas the subshells are the little rooms. You can think of them within the house. So you have your little house. Within there you have your little room, and those are going to be the subshells. Generally, subshells have different shapes. So you might remember from Gen Chem, you have your 1s, you have your 2s, which is slightly bigger version of the 1s, and then generally you also have your p's, your p orbitals, and those also have different dimensions, different sizes. You have the 2p, then you have the 3p, and so on and so forth, and those might actually be bigger. And obviously I'm going to go a little bit into that right now, but different subshells can accommodate different quantities of electrons. So a p might accommodate a different amount than a s, and so on and so forth. Now, orbitals. Orbitals are what the subshells are composed of, and I like to think of it as the furniture within those little rooms. That's how I like to think about it. So that's kind of the idea here. Now, without further ado, but how are these actually filled in? So now let's talk a little bit in depth about the subshells and a quick periodicity recap. Now, the period tells us the main energy levels / shells. So what do I mean by that? Well, here hydrogen would be the first, so N equals 1. But if I go 3 down, then Na is equal to 3. So that's essentially all I'm saying. So energy levels go down with the periods, and that will dictate their size indirectly, because as we remember now, the bigger the energy level, the further from the nucleus, the larger the radius. So that's just a trend you can remember, and we can keep going down. Now the groups, however, those tell us something slightly different. The groups, which is 1, 2, and then so on and so forth, you know what I'm saying, you just keep going down, those actually dictate something slightly different. The groups tell us the number of valence electrons. So this is very important because scientists, or chemists, shall I say, started noticing earlier, far earlier than 1800s, or even earlier than that. They started noticing that the group number, or shall I say, the number of valence electrons dictated a lot about what we care about in this course I'm about to teach, which is bonding and reactivity. So let's think, for instance, carbon has 4, nitrogen here would have 5, and this pattern actually keeps going. Oxygen has 6, fluorine has 7, and this will be important later, but you keep going down, whereas hydrogen has 1. Beryllium has 2. Now you notice that the transition metals, we kind of skip them because those are funny business, and we won't be delving too much into those in this topic, but I will be making a separate playlist on those. But how do we actually know which subshell we're in? Well, there's some very clear ways of filling these orbitals. And a memorization tool that you might have learned in Gen Chem is this one here, which is essentially this little pattern where you can follow, where you start here, and then you go here, and then you go here. And basically, we know from Gen Chem the different subshells have different number of electrons. So if we were to look at 1s, let's say for instance we want to fill the carbon atom. Now the carbon atom has a total of 6 protons and 6 electrons, which again, it's 1-to-1 for neutral atoms. So if we were to fill it in here, following those common Gen Chem rules, those names you might have heard of, Hund and Pauli exclusion principle, we know that energies are first filled and then we go up. So filling from the lowest energy level first with equal energy orbitals, fill them one at a time before pairing. That's Hund. And then Pauli exclusion basically just says that you can have the opposite spins within the orbitals, within the same orbital. You cannot have the same one. So if we were to fill in the carbon, which has 6 electrons, it would be this way: 1, 2, 1, 2, and then 1, 2. You notice I keep going down and I have not filled my subshell, so I won't start double sharing. One last thing I want to mention before we move on is that most atoms, or all atoms in general, want to fill a full octet rule. Now, this octet rule, they want to fill in their highest energy level, which in case for carbon, it is the 2, the second energy level. So we're missing how many? We're missing 1, 2, 3, 4 electrons. And that's why you will be making a lot of 4 bonds with carbon, and why it's known to be such an interesting atom, because it can make a lot of bonds. Now, I also want to mention something really fast, which is I briefly said that yes, you see this pattern. So if we kept going and going and going and going, you will notice that right when we get at the third energy level, the third period at Na, it is exactly when you actually reach the D subshell. And the 3D, like all the other Ds, can actually accommodate a total of 5 orbitals and 10 electrons. F actually can do a lot more. I'm not going to go into F right now, but it just keeps going up and up and up. I believe it is 14. I could be wrong on that, but please double check that. But in general, you're going to be dealing only with this type of subshells in organic chemistry. Now, there are different types of bonding, right? There's 3 main types of bonding, actually. There's metallic, covalent, and ionic. Metallic bonding, very briefly, is essentially metal atoms that share a mobile sea of electrons. And we won't focus much on that, because if you think about it, organic chemistry is really just a few of those atoms here, a couple of halogens, and of course there are some metals that we're going to be dealing with, but we won't be dealing with metal to metal bonds, which is essentially what metallic bonding is. It's when you deal with 2 metals. The reason why there's a sea of electrons, in case you're interested, is because metals have a very low ionization energy level, and because to feel that octet that we spoke about before, they actually lose 1. So for instance, Na will lose 1 because it is in the first group sense, is 1 electron in its outermost subshell. In this case, it's the S, because it wants to reach that, what we like to call the noble gas configuration. Just a fancy way of saying a full octet. And like in the case of carbon, it's just gonna be filling those in. Well, for Na, it just has to lose 1 and it will have that full octet. So anyways, covalent is where it gets interesting. Now, what happens when I put a nonmetal with a nonmetal? Well, let's just briefly talk about periodicity. We know a little bit about periodicity from Gen Chem, and I'm not going to go a lot into Seth and those things, but just in general, electronegativity is essentially increasing from the bottom left to the top right, with the most electronegative element being fluorine. And generally speaking, what tends to happen is large electronegativity differences will give you this ionic character that we're going to talk about here. But if you have very similar electronegativity, such as is the case in covalent bonds, what ends up happening is that they actually share electrons, and that's called covalent bonding. So covalent bonding essentially is the following. So let's say chlorine. If I did the little electron filling of chlorine, it would look something like this. Just speed up the correct way of filling them, and fill in 1, 2, 3, 4, 5. You note it is missing 1 electron to be happy. Hence what happens is that they end up sharing that electron like this, and they form a bond between that electron. You can think of it like this, you can think of it like that, like a Lewis structure. And in general, those some terms you might have encountered in Gen Chem, and all the chlorines are happy. They're both stable, and when sharing, they both feel equally that shared electron and their own. Hence, why they share. Now, ionic, however, is when you have a metal and a non-metal. So we just said before that metals like to lose electrons because they will become more stable by doing so, yet chlorine wants to gain one. So how are they both happy? Well, they literally donate an electron to one another. In this case, the metal will give it to the non-metal. And what ends up happening is that we end up with charges. You have a positive charge in the Na and a negative charge in the chlorine. And that is what bonding is about, because now the chlorine is going to be happy with that 8 electrons outside. And by the way, here we could imagine the bonding like here, right? So both chlorines are now going to be with their quote-unquote full happy octet. So yeah, we can think of it like that. So the octet is powerful too, because now we're going to be dealing with some very specific predictable atoms in organic chemistry. So let's say for carbon, I mentioned earlier that it wants 4 to fill that octet. So let's say that what happens if let's say get nitrogen, which to fill its octet will need, well, it has 5 outside, so it needs 3 more. It needs 3 shared electrons. It has to share 3 of its own to gain as if it was its own electrons. So carbon, however, it's gonna need a total of 4. So a very common situation that you'll see is hydrogens being the key. Because hydrogens, they're funny business, but they only have 1 electron outside in their 1s orbitals. So they tend to only form 1 bond. Now, this is one example of such a situation. What is going on here? You're like, why are you drawing so many lines? Well, you notice that I did this. I just made this molecule up. Well, there's a clear trend when drawing Lewis structures, and that's just following the octet rule. You see that each nitrogen here has a total of 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Whereas hydrogen, it only has 2 electrons. 1, 2, 1, 2, 1, 2, 1, 1, 2, 1, 2. That's because hydrogen is in the 1s, and the 1s, if you remember, the 1s only has 2 electrons to be filled, its own and the shared. So that's kind of one of the ways to start making molecules. Molecules happen because the carbons and the nitrogens and the hydrogens like to share to reach their full octets. And this is exactly what we're looking at here. We can do the same with other atoms. So let's say I'm playing around with carbon, and let's put a carbon here. Let's say that I put a carbon here, and you have 1, 2, 3, 4, 5, 6 electrons around that oxygen, and you have a carbon here. Let's imagine that there's some H's here. We already know that the H's are going to be sharing 1 and gaining 1. The carbon did the same with the hydrogens, and it has 1 left lone electron here that it's going to donate with the oxygen, and then the oxygen has 1 left to share to gain its octet. So now you know that the oxygen has 8. 1, 2, 3, 4, 5, 6, 7, 8. The hydrogens all have 2, of course counting for the shared in each atom. And then the carbons themselves also has 8 electrons. So everyone's happy here. Everyone's winning. Everyone has their full octet. Everyone's stable and happy. So the octet rule is a powerful rule. Okay, let's use some examples where this might actually come together. So for instance, H2SO4, these are some common molecules that you might see later on. The reason I want to start with this one is because there's exceptions to the octet rule. We'll talk a little bit down here about that, but HSO4 is such example, where the S actually doesn't need, it needs more than usual to fill its octet, and that's just because if you look at the periodic table, the S is actually in the 3rd row. And we discussed earlier before that once you get to the 3rd row, you actually start getting into the D subshells, and the subshells have 10 electrons. Hence, it starts cracking a little bit this hypothetical octet rule. It's not perfect, it's just something that a guide per se. But the other atoms that we're going to be talking about do indeed follow this octet rule, where hydrogen only needs 2, and oxygen tends to need 8 around, chlorine needs 8 around, and oxygen, nitrogen, and carbon. So for the S, how would it look? Well, this is a very common molecule you will have to do with a lot in organic chemistry, so you just know it off the top of your head, but it looks something like this. And let me fill the little electrons, but you'll notice that the S doesn't have 8 around it, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around itself, whereas the oxygen, well, all the others have 8, and the hydrogen has 2, as we usually saw in the patterns above. So yeah, that's kind of what's going on here. And just remember that the oxygen is in the 2p orbitals. Its highest is 2p. So it would be kind of like carbon, but instead of having something like this, if we were to draw the oxygen, it would look slightly different. It would look something like this, because it is how many ahead? I just want to get clear what we're actually doing, what we're filling this one's out. Oxygen has 2 more, so we jump 1, 2, and so you need 2 more electrons, so you would have 1, 2, and you're missing 2 more to fill that 2p, and that's why we tend to donate 2 electrons, so that we feel the pool from the sharing, quote unquote, of the other 2 electrons from the other atom. So that's just something to keep in mind. But what if we do the same for another molecule like O2, oxygen, which you know way too well? Well, that's how it looks like. And here we also know that each one has 8 electrons in their own respective way. So that's a stable molecule. Chlorine, we already did this above, so I don't have to re-explain it, but now we understand its stability. 8 electrons in each side. And then, that's a CH4, not a H4. There we go. How would CH4 look like? Well, we know that hydrogen has 4 electrons around. Each H wants to have 2 in total. 1 of its home to share, 1 to receive. And there we go. Anyways, there are exceptions. It is not a perfect rule. The octet rule, as I mentioned with sulfur, it is actually breaking down a little bit. Now, for boron and beryllium, it also breaks a little bit, but it is called hypovalent. So instead of being an excess of electrons around itself, it is actually less than 8. So hydrogen we already spoke about. It is kind of only 2 because of the 1s, but boron and beryllium is slightly different. Boron has something to do with the fact that it's got an empty p orbital, hence it's open to accept those excess electrons. But generally speaking, boron can make 3. It can be happy with 3 or with more. So another example of a molecule that we might see later would be something like this. So it can also be happy in another state. Now I won't talk about the charge right now, I'll talk about that in the next video, but generally I just want to keep in mind that it can be stable with only 1, 2, 3, 4, 5, 6 electrons around itself. Counting those, it is donating and accepting. So what about beryllium? Well, beryllium, it can be happy with 2, just with 2. 1, 2, 3, 4 electrons. So it's a weird situation, I know, but those are just 2 exceptions. Extended octets, such as the one as we spoke about, the sulfur above, the sulfur up here, the sulfur molecule, essentially it happens past the 3rd period, and we kind of spoke about that above here, but basically it opens up to a new whole situation where you can have 10 electrons. And that's why you can go beyond the octet rule, the regular octet rule, because now you're in the 3D subshell. And that happens the moment we get past to the 3rd period. So you'll notice everything below this line here can, in theory, accomplish a extended octet. Everything below this pink line. But happily, we will only be accommodating, well, we will be dealing with some of them, but we're primarily dealing with some more predictable atoms in organic chemistry, but as you will tell, there are obviously exceptions because we will be dealing with some of them below that pink line. Nonetheless, let's just look at some examples. So here are some common examples. I already wrote this one above, but yeah, there are some common examples for you to look at later. So don't be scared if you see something that breaks this rule. But yeah, that's kind of one way of drawing Lewis structures.